Hey class, this video is going to be on graphing linear inequalities. So hopefully by the end of this you can graph a line, you can graph a linear inequality, and you can rewrite linear inequalities into slope-intercept form. So let's start with some vocab. First of all, what is a linear inequality? Well, it's a linear function that contains an inequality. So linear function So an inequality is like a less than symbol, greater than symbol, less than or equal to, greater than or equal to. So those are our inequalities. So a linear equation has an equal, a linear inequality has an inequality symbol. So slope-intercept form, remember, is y equals mx plus b, where the slope represents the m. That's our rise over run. It's our rate of change. It's the change in y over the change in x. The y-intercept, that is our b value. It's an ordered pair that's always 0 and some y coordinate, and it's where the line crosses the y-axis. A solution to an inequality, and there's going to be multiple solutions, but a solution of an inequality is an ordered pair. So some xy coordinate that makes the inequality true. So how are we going to graph our inequalities? First, these are the steps. First, you want to rewrite to y equals mx plus b equation. Then we're going to graph the slope. Remember, m equals slope and b equals the y-intercept. So start by graphing the y-intercept and then the slope. Decide if you have a solid or dotted line. You draw a solid line when you have a less than or equal to or a greater than or equal to, because those points on the line are equal and part of your solution. You draw a dashed line if you have just less than or just greater than, because they're not equal. So the points along the line are not going to make our equation true. Then we pick a point not on the line to decide which way we shade. So we will do an example. So first, is it in the form y equals mx plus b? Okay, check. So then our slope is -2 or -2 over 1. That's sometimes helpful in graphing. And then we have a y-intercept of +5. Since our inequality sign is less than or equal to, it is going to be a solid line. Okay, so we're going to start at +5 and then a slope of -2. So I want to go down -2, right 1, +1. So -2, +1, -2, +1. Or you can go +2, -1 to make our line. Our line is going to be solid. And now we need to decide where we shade. So then we're going to pick a point to test. You can pick any point you want, not on the line, either side. So we have two sides. This is like the first half and the second half over here. You can pick either one. If the origin, the 0, 0 point is not being used, I like to use that because it's easy to plug in 0. So I'm going to test the point 0, 0. And that means I'm going to plug in 0 for x and 0 for y. So 0 is less than or equal to -2 times 0 plus 5. So is 0 less than or equal to 5? That is true. So that means that this point right here is a solution, which means that all of the points on this half are solutions. So I shouldn't have went over the line there, but everything below the line is a solution. So let's do one more here, and then see, can pick out a pattern. So is this one in y-intercept form? slope-intercept form, I mean. Yes, it is. Our slope is negative 2/3, and our y-intercept is positive 5 again. So 1, 2, 3, 4, 5. And then a slope of negative 2/3, you can go negative 2, positive 3, so down 2 over 3, down 2, right 3. Or you can go positive 2, negative 3, so up 2 over 3. Since this is a less than or equal to, again, we have a solid line because the points on the line are a solution. They will make the inequality true when you plug in those points. Like we got a true statement here. These points make the inequality true. The points along that line will make the inequality true. So, solid line. Sometimes it'll auto-correct it. And then since 0, 0 is not being used, let's test that point again. So 0 for y, 0 for x. So 0, anything times 0 is 0. 0 plus 5 is 5. And 0 is less than 5. This makes the inequality true, which means that these points below the line are solutions. So we're going to shade all of those points below. So now if you look at this here, the less than actually has something to do with that shading below. So it's always good to test a point. But if you really read this, this says that y is less than this line. And this is your y-axis here, your vertical axis. And it says that y is less than that line. So where is y less than that line? Down here. So it's all below. This one says y is less than that line. So again, here's your y. Y is less than the line down here. So you're going to shade below. So that's another way of thinking about it. These are a couple special case examples. So this one is in the form, slope-intercept form, except for that it's just a constant, which means that I have just a y-intercept. I do not have a slope given to me, so that means the slope is 0, because 0 times x plus 2 would just equal 2. So this is y greater than or equal to 2, so 2 is right there. It is a solid line again because it is greater than or equal to, so 2 is equal to 2. 2 is not greater than 2, so it's going to be a solid line there. And a slope of 0 is just a horizontal solid line. And then it says that y is greater than 2. Well, y is this vertical axis, and where is y greater than 2? Up here again. And so you could test 0, 0 if you wanted. And so you would plug in 0, 0. So is 0 greater than or equal to 2? And you would say no, so you'd shade the other side. So you'd shade it above. All the y values are greater than 2 or above that vertical line or that horizontal line. Now this one is a special case, x greater than negative 1. When you have an x equals line, this is a vertical line. Its slope is undefined. So x equals negative 1 is right here. Now this is just greater than negative 1. So negative 1 is not greater than negative 1. Negative 1 is equal to negative 1. So the points along this vertical line have to be dashed because they don't make the equation true. Negative 1 is not greater than negative 1. If you have $5 and I have $5, you don't have more than me. We have the same amount. So that's why it's dashed there. Then where are the values that are greater than negative 1? They're going to be to the right. So for this one, you're going to shade greater than, you're going to shade to the right. Less than, you would shade to the left. For there. You could test 0, 0. And so 0 is greater than or equal to negative 1 is true. Okay, a couple more. So these ones you have to rewrite in slope-intercept form and then graph the linear inequality. So similar to what we practiced yesterday with rewriting the equation, we want to solve for y. So the first thing we're going to need to do is take this 4x positive and subtract it from both sides. So that's going to give me 2y here greater than, and I want the x to come first in slope-intercept form, so it's going to be negative 4x, and then it was a positive 8. And then I'm going to divide everything by 2 to get y by itself. So y is greater than negative 2x plus 4. So then I have a dashed line because it's just greater than. I'm going to be shading above since it says y is greater than that line. And I have a slope of negative 2 or negative 2 over 1 and a y-intercept of 4. So that's going to look like this. We're going to go up to 4, slope of negative 2, so down 2 over 1, down 2, right 1, down 2, right 1, or you can go up 2, left 1. It's going to be a dashed line this time. And since the y is greater than the line and y is right here, so greater than is above, but you can still test it. So let's test 0, 0 since it's open. And I'm going to plug it just into, it doesn't matter, original or this one. So 0 is greater than negative 2 times 0 plus 4. So is 0 greater than 4? No. So 0, 0 does not make this equation true. It is not a solution. So we shade opposite. So we shade above. And it's all of these points. So an example solution to this equation would be anything in this shaded area. So like 3, 3, that's a solution. 3.51, that's a solution. Anything in that shaded area and in between are all solutions to this inequality. So it really has infinitely many solutions, but it's all above that dashed line. It doesn't include any points on that line. Okay, last one. And this is an important example because it shows you one more thing that you have to remember when solving with inequalities. So we're going to start by getting y by itself. Start by subtracting the 2x. So you get negative 3y is less than negative 2x and a positive 6. Then you have to divide by negative 3. And so something you need to remember is that when you divide by a negative number, you have to flip the inequality. So if you divide by a negative number, you have to flip the inequality. So we got y is greater than, and then negative over negative is going to be positive 2/3 x, and then minus 2 if I reduce those fractions if I can. So this time I have a dashed line again, and I should be shading above because it's y is greater than that line. I have a slope of 2/3 and I have a y-intercept of negative 2. So y-intercept of negative 2 and slope of 2/3. So I'm going to go up 2 over 3, up 2 to the right 3, up 2 to the right 3. Or I can go down 2 to the left 3, and then I wanted a dashed line. I should be shading above because y is greater than that line. But let's just test 0, 0. And we'll have 0 greater than 0 minus 2. So is 0 greater than negative 2? Nope. So we will shade above. And all of those points in the shading are solutions to this inequality except for the points that are on the line since it's dashed. And then you have to remember to flip the inequality if you end up dividing by a negative. So not if you subtract and not if you add, but only if you multiply or divide by a negative, you switch the inequality. So, for example, we all know that 8 is greater than 4. But if you divide both sides by negative 2, you get negative 4 greater than negative 2. Now that's not true anymore. So if you divide by a negative, you'd have to flip this because negative 4 is less than negative 2. So that's how that works and why we have to do that. All right. Thanks for watching.